A three-phase electrical system consists of three live conductors, labeled A, B, and C, along with the neutral conductor N. In a balanced three-phase system, the voltages between any two of the live conductors are 120 degrees out of phase. The voltage between each live conductor and the neutral conductor is 120 volts. To derive 120/208 single-phase power from a 208Y/120 three-phase system, you need to connect the appropriate live conductors and the neutral conductor to a separate single-phase circuit. Let's assume you have a meter-pack meter center with the following connections: live conductors A and B connected to terminals N and H2, and the neutral conductor N connected to terminal N. Now, let's examine how the 120 volt and 208 volt phases are obtained. The voltage between terminal N and terminal N is the same as the voltage between live conductor and the neutral conductor in the three-phase system, which is 120 volts. This is expressed as voltage N equals voltage A, N equals 120 volts. The voltage between terminal N and terminal H2 is the voltage between live conductors A and B in the three-phase system, but with a phase shift of 120 degrees. The magnitude of this voltage is 208 volts, which represents the line-to-line voltage. This can be represented as voltage N H2 equals voltage A, B equals 208 volts with a 120 degree angle difference. Therefore, by connecting live conductors A and B to terminals N and H2, and the neutral conductor N to terminal N, you can obtain a 120/208 single-phase circuit. It is crucial to properly connect the ground conductor for safety. The power factor and load balancing of the single-phase circuit should also be considered to ensure efficient operation. It is essential to consult with a qualified electrician for proper installation and to ensure all safety precautions are followed. The derivation of 120/208 single-phase from a 208Y/120 three-phase system involves understanding the phase relationships within the three-phase system and how to tap into specific line-to-neutral and line-to-line voltages. The 208Y/120 volt system is a Y-connected system, meaning the three phases are connected to a common neutral point. This configuration provides both 120 volt and 208 volt options. The 120 volts is the voltage from any one of the three phases to the neutral. The 208 volts is the voltage between any two of the three phases. When deriving a 120/208 single-phase service, you are essentially creating a single-phase system that can provide both 120 volt and 208 volt circuits. This is commonly used in applications where you need both standard 120 volt outlets and higher voltage 208 volt appliances or equipment. To understand the mathematical relationship, it's important to remember the properties of a balanced three-phase system. In a balanced system, the three-phase voltages are equal in magnitude and are separated by 120 degrees in phase angle. If you consider one phase as the reference, the other two phases will be at 120 degrees and 240 degrees relative to that reference. Let's denote the three-phase voltages as VA, VB, and VC. If VA is the reference at 0 degrees, then VB is at 120 degrees and VC is at 240 degrees. The line-to-line voltage, which is the voltage between any two phases, is calculated as the vector difference between the two phase voltages. For example, the voltage between phase A and phase B, VAB, is equal to VA VB. Mathematically, this can be represented using complex numbers. If VA equals 120 volts at 0 degrees and VB equals 120 volts at 120 degrees, then VAB can be calculated as VAB equals 120 volts at 0 degrees, 120 volts at 120 degrees. Converting to rectangular form, VA equals 120 plus J0, and VB equals 120 asterisk cos 120 degrees plus J asterisk 120 asterisk sin 120 degrees equals minus 60 plus J 103.92. Therefore, VAB equals 120 plus J0 minus 60 plus J 103.92 equals 180 J 103.92. Converting back to polar form, the magnitude of VAB equals square root of 180 squared plus minus 103.92 squared equals approximately 208 volts. The angle of VAB equals arctangent minus 103.92/180 equals approximately minus 30 degrees. So, VAB equals 208 volts at minus 30 degrees. This shows that the magnitude of the line-to-line voltage is 208 volts, which is the value you obtain when measuring between two phases in a 208Y/120 system. When setting up a 120/208 single-phase service, you are tapping into one of the line-to-line voltages, such as VAB, VAC, or VBC. This provides the 208 volts. You are also tapping into one of the line-to-neutral voltages, such as VAR, VB, or VC. This provides the 120 volts. The key is to ensure that the connections are made correctly and that the loads are balanced as much as possible to avoid overloading any one phase. A meter pack center is designed to facilitate these connections and provide a convenient way to distribute the power to multiple tenants or users. Firstly, understanding the three-phase system is crucial. In a three-phase system, the three voltages are generated 120 electrical degrees apart. This means that the voltage waveforms are offset from each other, providing a more consistent power delivery compared to a single-phase system. The 208Y/120 volt configuration is a common type of three-phase system, where the Y indicates that the three phases are connected in a Y configuration, with a neutral point at the center. The 120 volts is the voltage from any phase to the neutral, and the 208 volts is the voltage between any two phases, often referred to as line-to-line voltage. Secondly, deriving the 120/208 single phase involves tapping into the appropriate voltages from the three-phase system. To obtain the 120 volts, you simply connect to one of the phases and the neutral. This provides a standard 120-volt single-phase circuit for lighting outlets and other common appliances. To obtain the 208 volts, you connect to two different phases. This provides a higher voltage single-phase circuit that can be used for larger appliances such as electric stoves, dryers, and air conditioners. The mathematical relationship between the phase voltage 120 volts and the line-to-line voltage 208 volts in a balanced three-phase system is given by the equation line-to-line voltage equals square root of 3 multiplied by phase voltage. In this case, 208 volts equals square root of 3 multiplied by 120 volts, which is approximately equal to 1.732 multiplied by 120 volts. Thirdly, a meter pack meter center is specifically designed to facilitate the distribution of power from a three-phase system to multiple single-phase services. It typically consists of a main three-phase panel that receives the incoming power from the utility. From this main panel, individual meters are connected, each providing a separate 120/208 single-phase service. Each meter is connected to two of the three phases and the neutral, allowing it to provide both 120-volt and 208-volt circuits to the tenant or user associated with that meter. Fourthly, it's crucial to ensure that the loads are balanced across the three phases of the system. This means that the total amount of current drawn from each phase should be as equal as possible. If one phase is heavily loaded while others are lightly loaded, it can lead to voltage imbalances, overheating, and other problems. The meter pack meter center typically includes features to help balance the loads, such as load monitoring and phase rotation. Fifthly, safety is paramount when working with electrical systems. Always ensure that the power is turned off before making any connections or modifications. Use properly insulated tools and equipment, and follow all applicable electrical codes and regulations. It's also important to have a qualified electrician inspect the installation to ensure that it is safe and compliant. Sixthly, consider the power factor of the loads being connected to the system. Power factor is a measure of how efficiently electrical power is being used. A low power factor can lead to increased current draw and reduced system capacity. Correcting the power factor can improve the efficiency and performance of the system. Seventhly, the neutral conductor plays a critical role in the 208Y/120 system. It provides the return path for the current and helps to maintain a stable voltage. It's essential to ensure that the neutral conductor is properly sized and connected to avoid voltage drops and other problems. Eighthly, grounding is another important safety consideration. The grounding system provides a path for fault current to flow back to the source, helping to protect against electrical shock and equipment damage. The grounding system should be properly installed and maintained to ensure its effectiveness. Ninthly, when selecting equipment for the 120/208 single-phase service, it's important to choose components that are rated for the appropriate voltage and current. Using undersized or improperly rated equipment can lead to overheating, failure, and even fire. Tenthly, regular maintenance is essential to ensure the continued safe and reliable operation of the electrical system. This includes inspecting connections, checking for loose wires, and testing the grounding system. Addressing any issues promptly can prevent more serious problems from developing. The derivation of 120/208 single-phase power from a 208Y/123 phase system involves understanding the principles of three-phase power, the mathematical relationships between phase and line voltages, and the proper connection and distribution of power using a meter-pack meter center. It's crucial to prioritize safety, load balancing, and regular maintenance to ensure a reliable and efficient electrical system. Transformation from a 208Y/123 phase system to 120/208 single-phase system involves several key concepts and practical considerations. Firstly, understanding the vector relationships in a three-phase system is essential. In a balanced three-phase system, the three-phase voltages are equal in magnitude but are displaced by 120 degrees in phase from each other. This 120-degree displacement is what allows for the high line-to-line voltage. When measuring from any one phase to the neutral line to neutral, the voltage is 120 volts. However, when measuring between any two phases line to line, the voltage is 208 volts. This 208 volts is not simply the sum of two 120-volt phases, it's the vector sum, which takes into account the 120-degree phase difference. Secondly, the mathematical derivation of the 208-volt line-to-line voltage from the 120-volt line-to-neutral voltage is based on trigonometry. In a balanced three-phase system, the line-to-line voltage is equal to the line-to-neutral voltage multiplied by the square root of 3, approximately 1.732. This can be expressed as VLL equals square root of 3 multiplied by VLN, where VLL is the line-to-line voltage and VLN is the line-to-neutral voltage. In this case, 208 volts equals square root of 3 multiplied by 120 volts. This mathematical relationship arises from the geometric properties of the voltage vectors in a three-phase system. The three-phase voltages can be represented as vectors in a complex plane, and the line-to-line voltage is the vector difference between two of these phase voltages. The magnitude of this vector difference is equal to the line-to-neutral voltage multiplied by the square root of 3. Thirdly, the configuration of the 208Y/120 system plays a crucial role in the derivation of the 120/208 single-phase system. The Y in 208Y/120 indicates that the three phases are connected in a Y configuration with a common neutral point. This neutral point provides a reference for the 120-volt line-to-neutral voltages. The line-to-line voltages are taken between any two of the three phases. By tapping into the appropriate phases and the neutral, it is possible to create a 120/208 single-phase system. Fourthly, a meter-pack meter center is designed to facilitate the distribution of power from a three-phase system to multiple single-phase services. It typically consists of a main three-phase panel that receives the incoming power from the utility. From this main panel, individual meters are connected, each providing a separate 120/208 single-phase service. Each meter is connected to two of the three phases and the neutral, allowing it to provide both 120-volt and 208-volt circuits to the tenant or user associated with that meter. Fifthly, when connecting the 120/208 single-phase service to the meter-pack meter center, it is essential to ensure that the connections are made correctly. The 120-volt circuits are connected between one of the phases and the neutral, while the 208-volt circuits are connected between two of the phases. It is also important to ensure that the neutral conductor is properly connected and sized to handle the expected load. Sixthly, load balancing is a critical consideration when distributing power from a three-phase system to multiple single-phase services. Ideally, the load should be distributed evenly across the three phases to minimize voltage imbalances and prevent overloading any one phase. The meter pack meter center may include features to help balance the loads, such as load monitoring and phase rotation. Seventhly, safety is paramount when working with electrical systems. Always ensure that the power is turned off before making any connections or modifications. Use properly insulated tools and equipment, and follow all applicable electrical codes and regulations. It is also important to have a qualified electrician inspect the installation to ensure that it is safe and compliant. Eighthly, consider the power factor of the loads being connected to the system. Power factor is a measure of how efficiently electrical power is being used. A low power factor can lead to increased current draw and reduce system capacity. Correcting the power factor can improve the efficiency and performance of the system. Ninthly, the neutral conductor plays a critical role in the 208/120 system. It provides a return path for the current and helps to maintain a stable voltage. It is essential to ensure that the neutral conductor is properly sized and connected to avoid voltage drops and other problems. Tenthly, grounding is another important safety consideration. The grounding system provides a path for fault current to flow back to the source, helping to protect against electrical shock and equipment damage. The grounding system should be properly installed and maintained to ensure its effectiveness.